All right, welcome back. Now that we have an overview of the filters, as well as an understanding of filter routing and the capabilities therein, it's time now to talk about the different types of filters that come with Massive. So I'm going to go up here to filter number 1, and if I click on this drop-down menu, I can see all the different types of filters that I have. I have 2 low-pass filters, 2 high-pass filters, an all-pass, double-notch, band-pass, band reject, scream, daft, comb, and acid. We'll go through each of these. So with the low-pass filter, I have 2 options. I have a low-pass 4 pole and a low-pass 2 pole. What do those numbers mean? Well, the 4 means it is a 24 decibel per octave filter slope, and I'll explain that in just a moment. The 2 is a 12 decibel per octave. High pass 4 would be 24 decibels per octave and 12 decibels per octave here, and we'll talk about that in just a moment. So let's select the low pass 4 pole and hear what's going on here. So what is a low pass filter? A low pass filter is, just as its name implies, a filter that will allow lower frequencies to pass through and will forbid higher frequencies to pass through. And you may be asking, well, how do you know which frequencies get to go through and which don't? The answer to that is determined by this cutoff knob here. You can see with these filters, the middle knob, this is a bandwidth knob with other filters, but with low pass, it's not applicable, so this won't do anything. And then we also have a resonance knob, and I'll explain resonance in just a moment. So the cutoff knob determines the frequency at which the sound begins to be cut off by that filter. So with a low-pass filter, if I have my cutoff knob all the way down at the left, you're going to get an almost inaudible sound. So I need to set up my routing in order to demonstrate how this works. So I'm only going to have oscillator 1 active. I'm going to send it completely to filter 1, and then I'm going to put these in series and deactivate filter 2. So that I'm just dealing with filter 1, and I'm going to turn my filter mix all the way up. This is just me saying, take all of this audio signal, send it to filter 1 only, and then output the output from filter 1 only. So when I play a note now, you can barely hear anything. You can see up here a voice is registering, but you can barely hear anything. And that's because my cutoff frequency is all the way down at the bottom, at the very, very lowest it can go. So only the very, very low frequencies are passing through this filter, which means that we can barely hear them. If I move this up, you'll start to hear a dull sound. Some of the mid-range frequencies are coming through now. And then when I raise it all the way to the top, it sounds about normal, like it would if there was no filter applied at all. You can hear the difference there when I activate and deactivate this filter. So this cutoff frequency is me telling this filter where in the frequency spectrum to start dropping off that sound. And since I've selected the 4-pole, then that slope where it's dropping off is at 24 decibels per octave. So it's a steeper, sharper slope. So, for example, if you want to create a bass sound, you might drop this down an octave, set it on square wave, and have your cutoff frequency about right here. Turn my resonance down. And it's sort of starting to sound a little bit like a bass. So that leads me to describe the resonance knob. The resonance is a little bump in the frequency spectrum where that cutoff frequency has been assigned. So if you think about it, looking at a channel, the parametric channel equalizer readout or something of the frequency spectrum, whenever I move this, I can have a little bump at that cutoff frequency by boosting up this resonance. So if it's up all the way to the top, it's going to create this really squelchy, bad sound. I mean, there's a place for that sound, to be sure, but this will help make the cutoff frequency make more sense. So if my resonance is up high, then now you'll really be able to hear the movement of this cutoff frequency. And you can visualize that as being this little peak moving up and down the frequency spectrum when I adjust the cutoff frequency. Okay, so that's what the resonance does. It just gives a boost around the cutoff frequency. So we've gone over the low pass. Now, what do you imagine the high pass filter might do? Well, if you guess that it allows high frequencies to pass through, then that is correct. So similar to the really the opposite of the low pass filter is the high pass filter. It allows higher frequencies to pass through it, but it filters out the lower frequencies. That means that if my cutoff knob is all the way at the left, I'm probably not going to hear any difference than if this filter wasn't active at all. And that's because I'm only filtering out the very, very, very low frequencies that you can't even really hear anyway. But as I increase this, you'll hear those lower frequencies dropping out, and as it goes all the way to the top, you'll hear just the high frequencies coming through on the other side. Until you can barely hear anything because the frequencies that are passing through are so high. And once again, you have the 4-pole and the 2-pole, 24 decibels per octave slope, 12 decibels per octave slope. So those are the low pass and high pass filters. Those are the most common filters, and probably the ones that you'll be using the most often to shape your basic sounds. So now let's move on to the all-pass filter. The all-pass filter allows all frequencies to pass through. However, the phase of the signal on the other side of the filter is inverted. So when I move this cutoff frequency, you can hear it sound almost like a guitar pedal phaser. And it actually functions similarly to the phase modulation oscillator that we've already talked about. That's the all-pass filter. So the double notch filter is a little bit different. The double notch filter actually has two cutoff frequencies where it will filter out a portion of the frequency spectrum in two places rather than just one like the other filters that we've talked about. So as I move this cutoff knob, I'm actually moving two filtered sections on the frequency spectrum. So the band pass and the band reject filters are sort of opposites, and both of them have a 12 decibel per octave slope on either side of the cutoff frequency. So the band pass filter allows only a portion of the frequency spectrum to pass through in the middle. And of course, the middle would be wherever you set the middle to be using this cutoff knob. The opposite is true with the band reject, in which a portion of the frequency spectrum in the middle will be filtered out, and then the frequencies on the left and the right of that remain. So that's the band pass and band reject. And you can just think of that as, with the band pass, you're letting a certain bandwidth pass through, and that hump in the frequency makeup will be, wherever you set it to be. Band reject is you're rejecting that same bandwidth in the middle. And with both the band pass and the band reject, you can create the width of that band using this center knob here. So if you have it up at the top, then you have a nice wide hump. If it's low down here on the left, then you have a really narrow hump. Okay. So actually, let's listen to those and see how they sound. Choose the band pass. And we'll have a very small bandwidth with a high resonance, so this will be an extreme sound here. You can hear the thinness of that because I'm just allowing just a very small bandwidth to pass through this filter. If I make it larger, like this, then it will be a little bit softer and a little bit fatter of a sound. You can hear that like that, okay? Same thing is true with the band reject. It's harder to hear the difference there because you're only filtering out such a small portion of the bandwidth that your ear doesn't really pick up on it too much. But you can hear that there a little bit like that. So that's the band pass and band reject. The scream is a type of low-pass filter, but it has some feedback added to it, and that's why they call it scream, because it just sounds a little bit saturated and distorted. And so, this middle scream knob will control the amount of that feedback that's cycling through in the filter. Sounds nice and dirty and just kind of analog. The Daft is similar. It's also a low-pass filter, but it's got some extreme resonance settings here. Okay, and the comb filter is pretty crazy. It is a comb filter has multiple notches, and so it looks like the teeth on a comb that you that you comb your hair with. But in Massive, you have this pitch knob, a damping knob, and a feedback knob. So just like the Daft filter, or the Scream filter, in which we have some scream, which is the feedback. The comb filter has a feedback knob as well. It has a damping control, and then you can set the pitch, which is kind of like setting the cutoff frequency. And you can get some really crazy effects when the feedback is up high, and you can modulate the pitch like this. That's the comb filter. And then lastly, you have an acid filter, which has some quite extreme resonance. So that is the acid filter. So those are some of the different filter types. Play around with those, and we'll revisit them when we're designing our sounds later on. But it's good for you to know how they work and what's going on there. Okay. Thanks very much. See you in the next lecture.